Okay. So, welcome back. This is only the second lecture. Typically, for like the first week, I usually send the links pretty early. So the reason for that is, just to get you all used to how this goes. But starting next week, my links will go out more like 5 minutes, 5 minutes prior to lecture time. And so that also means you'll only get 5 minutes of the nice tunes, but that's a sacrifice I guess we'll have to make. So anyway, so typically if you're watching these videos later, then obviously it's pretty easy to just fast forward the video till when I crack open the do, or I guess when I start talking. Anyway, so. Last time I'd mentioned very briefly this kind of the very, very basic stuff of setting up, discussion of talking about points in space, right? That's literally all we did. So we did points in space, and we did the analog of, the equation for a circle in the plane that we got from the distance formula. From between 2 points in the plane. So similarly in space, we were able to do the same thing. We had notion of distance between 2 points in space. And this is going to be important for what I'm going to talk about today, because today what I want to talk about are vectors. So many of you will have encountered vectors in some form from somewhere else. A lot of times, the first place you encounter vectors is physics. And so what is a vector? Now, if I say this, what's a vector? The easiest answer, it's also true, is that a vector is an arrow, right? So what is a vector? A vector is an arrow. Now, in this case, if my paper is the plane, then this is a vector in the plane. We'll also talk about vectors in space. In fact, primarily is what we're going to talk about, vectors in space. But today, you'll see an example of a recurring theme in this course, which is whenever I want to draw something or make sense of something, typically the picture I draw is in the plane first. And then when I talk about a drawing that I make in space, I like to, mention the comparison to the plane, but just because it's easier to draw things in the plane. So a lot of times it can be hard to unpack what's going on in a 3D picture. So making some drawing in the plane is typically the way to go about it. Makes your life a whole lot easier. So anyway, so a vector is an arrow, and what I mean by that is that there's two quantities, right? So a vector, this is, you call this a definition even. A vector. Notice I'm not going to actually specify whether it's in R2, R3. It can actually be in whatever. Maybe I'll just go ahead and say that in R2, R3, so in the plane, in space, or in some general in space, which we're not going to talk about in this course, but just know that this can be generalized, and it doesn't really make a huge amount of difference here. But a vector, whether we're talking about plane space or some other higher dimensional space, a vector is an arrow. Now, if I just stop there, that might be a little mean. So when I say that a vector is an arrow, i.e., it contains two pieces of data. All right, and the two pieces of data it contains are length. That is literally how long this arrow is. Okay, so if I break out a ruler and I measure it, right, however long that thing is, looks like I drew a roughly 1 inch long vector in that case. However long that thing is, that is the length of the vector, and direction is encoded by the direction the arrow is pointing in. So it's two pieces of data, length and direction. Okay. All right, so that's all it is. Now, here's the thing, right? Automatically, the second that I say it's two pieces of info, length and direction, already you have some questions. So one, note that it doesn't actually refer anywhere to where this vector is sitting, right? So maybe I even draw a point here, right? And maybe I label that point P, and I draw another point and label that Q. So for a vector drawn in this way, P would be the initial point of this vector, and Q would be the terminal point. Now, me using those words to denote P and Q, that's giving me direction, right? So where does direction come in? Direction is me saying that this vector goes from P to Q. P is the initial point, Q is the terminal point. So this vector is going from P to Q. The arrow is going in that direction. Okay, so that takes care of direction. But what about length, right? So if direction is given by which of these points is initial and which is terminal, what is the length given by? The length is just given by the distance from P to Q. Note the length of the above vector. And let's give this vector a name. So let's call this vector the vector PQ. And I draw an arrow over it, right? The second I draw this, you automatically know what this means, right? So it's a vector. It has initial point P, terminal point Q. That's the direction it's going in, right? From P to Q. So note the length of the vector PQ is just the distance from P to Q. Or from Q to P, since we know that distance is symmetric, right? It doesn't actually matter which of those. So, Olivia, wouldn't the arrow already show direction? Yes, yeah. So, the point is that, obviously here's where it is nice, of course, to always have a vector in front of you, but you know that it would be a little bit cumbersome in a textbook to have every time a vector is referred to, just have a picture of the thing, right? It's easier to describe it. Ideally, here in a second, we'll see using coordinates. And so there's not going to be a picture showing you the direction. So then you got to get the direction from somewhere else. And so the way we're going to get the direction is by specifying 2 points and telling which one is the initial point and which one's the terminal point, which is the first and which is the second. Okay, so note the length of PQ is just the distance from P to Q. So if these 2 points have coordinates, right? So we'll say that this is in the plane. So our first examples of vectors in R2. So let's have point, we'll call this x1, y1, and we'll call the point Q, we'll say that it has coordinates x2, y2. Okay, then what is this distance? So the length of PQ, we will write this as the following. We will write this as the length of PQ here, right? So this is called the norm of the vector PQ. Or just the length of the vector. So, I will use these words interchangeably. In fact, I'll probably use length more than calling it the norm. So it's the length of the vector PQ just as well. Okay, and of course, what is this if I've assigned these 2 coordinates using our distance formula from last time? This is the square root of, so x1 minus x2 squared plus y1 minus y2 squared. Now maybe you fuss at me a bit and you say, wait, shouldn't this be reversed? Of course it doesn't matter because we're squaring both of these things, but for the sake of, well, that's the way you saw the distance formula, and also for the sake of what I'm going to do here in a little bit, I am going to reverse these things. So of course I'm doing nothing here. Don't think I'm doing anything. These 2 things are completely the same. I'm going to write it this way just because this suggests something I'm going to do here in maybe like 2 minutes. Okay. So this is what the length of that vector PQ looks like. Okay. Now, this is all fine, but there's another thing that comes up immediately. which is a vector consists of two pieces of info, length and direction, and that's it. Notice length and direction was all that was stated, and not say where this vector sits, right? So what do I mean? Imagine you have this vector and then you moved it down here, right? So it was up here, now you've moved the vector, you've translated it, say, down here. Okay, of course these 2 points you've changed. They're not P and Q anymore, they're like P prime and Q prime. They're different points, right? But did the length of that vector change? If I took here, let's do it on a blank sheet, right? If I take some vector that looks like this, oh, I'm off screen. If I take some vector that looks like this, oh, and I move it, right? If I move that vector like this, did I change the vector? Now, before you get too crazy, what if I took the vector and I did this? Does that change the vector? Okay. So, a vector is length and direction. Okay, if I were to take this vector and apply this transformation, which is a rotation, and why rotate it about this point? Let's just rotate it about the initial point. Of course, it doesn't matter, but it's rotated about the initial point. Does this change the vector? Well, it changes the direction, right? So if I'm rotating it, it changes the direction of the vector. So one of those two things is changed. Okay, so that kind of transformation changes it. If I were to take this and flip it, right, like across a mirror, if I were to draw a line of reflection here and reflect it across that line, that would change it as well because it would change the direction, right? But if I were to translate it, that doesn't change the direction, right? Direction is still the same. Okay, so direction is still the same. Does it change the length? Well, none of those things I did change the length, right? So rotating it, reflecting it, that didn't change the length of the vector. And certainly translating also does not change the length of this vector. Okay, and so what does that mean? So going back here, what does that mean? Well, it means that it doesn't matter where a vector sits, right? Well, if it doesn't matter where a vector sits, if I can take any vector here, right, that's sitting somewhere out in the plane, I can translate it wherever I want to, and it's the exact same vector. Okay, it's the exact same vector because the only two things we care about in a vector is length and direction, and those things are unchanged. So, if I can translate this to be wherever I want to, where is a really nice place that I might want it to sit? Right, where's a nice convenient place that I might want it to sit? Well, a nice convenient place that I could want it to sit is with its initial point at the origin. Okay, so this means we could consider any vector to have initial point, the origin, and terminal point, some other point, right? Okay. So, right, and I'm glad everybody was spamming origin. That's good. So that's the exact idea. So we can move it so that the initial point's the origin, the terminal point is some other point. And so what that means is, oh, okay, I don't need to make it look too nice. So in the plane, what that would mean is that that vector that I was just moving around might actually look like this. So I've moved P to be the origin, and Q is some point here. I'll call it Q prime, just to indicate it could be different than the Q that we started with. But it's some point, the direction is the same, and the length is the same. Okay, and so, in fact, here's some other point, right, that is the endpoint of a vector. Here's another vector. Here's another one. Here's yet another one, and so on. Okay, so there's a bunch of vectors that were sitting somewhere out in the plane, and then we moved them, okay, to have initial point the origin, and then they have terminal points somewhere, right, somewhere out here. Here's one more, just to do it. Okay, well, if all these vectors, if we can take any vector we come across and consider its initial point sitting at the origin, then that's not telling us much, right? The initial point is not really telling us anything, since we can always consider that to be the origin. So then what is determining the vector are these endpoints, the terminal points. Okay, so if you know that you can consider every point, every vector is, emanating from the origin, then it's the terminal point that determines the vector. And so here is the key fact, and even though this might seem obvious after this discussion, it's something that I will continue to mention because it's very important. And you'll see this mentioned, when you encounter this in linear algebra or any other context in which you encounter this. So vectors are just points, and points are just vectors. What do I mean by that? So vectors in R2 are just points in R2. That is what is meant. Of course, that is true in R3 as well. So vectors in R2 are just points in R2. And points in R2 are just vectors in R2. This statement is exactly the same if you replace R2 with R3. Okay, it's actually the same if you replace R3 with Rn. Okay, what do I mean by this? Well, let's see how it goes in both directions. Okay, so let me draw a vector. So first, I'm going to draw. This. Okay, this is my origin in the plane, and let's take a vector. I'm going to make it. How long do I want to make this in? Let's draw some like 1-inch vector. Let's say that it is this thing. Okay, so here's my vector. Okay, PQ. Okay, so here's vector, and I want to see how this vector is really a point. Right? Because you look at that and you say, wait, that's not a point, that's an arrow, right? It's a vector. It's definitely different than a point. So where does the point come from that I'm talking about? So I take this vector, I translate it to the origin. Of course, how do I do this translation? So if you like, I can draw a dashed line here, and I can translate this thing. So you can imagine me taking this vector and sliding it right down that line, translating it to right there, the origin. Okay, so let's look at our translated vector. And so P goes to P prime, which is just the origin. Okay, and Q goes to Q prime, which is some point. That point is the point associated to this vector. Okay, similarly, I can say, go backwards, right? I could start with a point, right? So let me draw my axes again. So let's start with a point. So here's a point. Okay, so what is the vector associated to that point? Since points are just vectors, it's the obvious one. It's the one emanating from the origin going to that point as its terminal point. There it is. Okay, so every point in the plane is a vector. Every vector in the plane is a point. So vectors are points and points are vectors. Okay, and so in fact what makes this nice is this gives us a convenient way of writing vectors. This gives us a convenient way of writing vectors. Okay, i.e. we write them as points. Okay, so to see an example. So I'm writing a vector as a point. Say here's my axes. Let's look at the vector v. And let's say my vector v looks like this. Okay, and I write vector v like this. When I write a vector, I will, to show you that it is a vector, I will basically write this little arrow over it. In physics, you might see like a hat written over it. So I will typically write arrow. A hat is used for something different typically. So when you take 240 or 461, you'll see. So linear algebra, you'll see that the little hat denotes something different typically. But anyway, this is really just because in writing I can't make boldface. Right, so if I had a way of conveniently writing a boldface v, then that's what I would do, but I can't. So there it is. It's a vector, and of course we're about to see why you would want, in general, to have a quantity distinguished as a vector rather than something else. Okay. So anyway, if here's my vector v, then this vector v has this point associated with it. Right? What is that point? Let's say in this case the point is like 3, 1. Right, in the plane. Then we actually just say the vector v is the point 3, 1. Right. So that's how we'd write. Here's another example, real quick. So here's a 3D example. So the same thing we did in the plane. I'm not going to go through the process of making any drawings or anything, but the same idea that we used in the plane to say that a vector in the plane was just a point in the plane shows that a vector in space is just a point in space. So I'm going to take this point here in space, and to see kind of where I intend this point to be located, here's here. Sorry, I did a bad job there. Forget that. Okay, so here's my point. We'll say this is here. So here's my x, here's my y, here's my z. What does this look like? So this is, we'll say this is the point, 4. Let's see. So 4, 1, 3. That looks about right. Okay, and so the vector going from the origin in space pointing to this point as its terminal point, we'll call that vector, say, w. That is associated to that triple, that point, 4, 1, 3. Okay. All right, if you have any questions about that, you can let me know. But here's the idea. Now, why is this nice? So why is this great? This allows us to easily define algebraic operations on vectors. Okay. Sterling, that only works when the vector is located at the origin. That's right, but of course remember that any vector you encounter anywhere can be put at the origin. So for all intents and purposes, you can consider every vector sitting at the origin. And if you have a vector sitting somewhere else, well, then you can move it to the origin. And I'm going to talk about exactly how we do that. Okay, so I'm going to go back to that in just a second. So this allows us to easily define algebraic operations on vectors. So we're going to have notions of adding two vectors, subtracting two vectors. When it comes to the question of multiplying, however, it's going to be a little bit trickier. Okay, and so for instance, we have vector addition. Okay, so For now, I'm going to repeat some of this notation, but in general, when I draw a vector, or when I write down a vector, this is the notation I mean. So let's say that we have two vectors in R3. So let U and V be vectors in R3 in space. Okay, and the notation that I mean is we'll say that we'll say that U has three components, U1, U2, U3, and V has three components, V1, V2, V3. Now, just to remind you, so these are called the components of the vector. So these are called the components of the vector. Okay. All right. Is 413 always XYZ? Yes, that's always how it is. So we always keep this consistent so that exactly there's not that kind of confusion going on. Okay. So U and V are vectors in R3. Here's U and V. What is the vector sum of these things? So what is U plus V? Well, U plus V is the vector that I get when I take each of these components and add them together component-wise. So I take U1 and V1, the first components of U and V, and add them together, and that's the first component of U plus V. The second component of U plus V is the second components of U and V added together. And last component, same thing. Okay. Now there's a similar version in R2. I'm going to write it once and then I'm not going to write the R2 version again because everything I do in this way is going to be assumed to go through in the same way. So if U and V are in R2 instead, right, and U then is U1, U2, and V is V1, V2, then U plus V is U1 plus V1 in the first component and U2 plus V2 in the second component. Okay, so that's exactly how that works. All right, dot product comes later. And that's going to be one of the products we talk about. Okay. All right, so here's what vector addition looks like. Now, vector addition is nice. Let's do a quick example of vector addition. So, an example, let's say let U be the vector, say -1, 5, 7. And let V be the vector -2, -2, 3. Right. Then U plus V is -1 plus -2, that's -3. 5 plus -2 is 3. And 7 plus 3 is 10. Okay, so simple enough. But the question is, what does this mean? Why is this useful? So we're going to talk about in a second that there are a number of ways that you could define certain operations on vectors, but we actually only care about the operations that are useful. Useful meaning they have some properties that are really nice. Okay, so vector addition is actually really nice. Now, you might not be able to exactly see that it's nice in 3D, so let's see what happens in the plane. There's a nice geometric interpretation of what's going on in the plane here. Should I do this before I talk about subtraction? Maybe not. Let's talk about vector subtraction. Actually, I want to talk about something else before I talk about vector subtraction. So I want to talk about scalar multiplication. Okay. So, if I want to talk about scalar multiplication, you might say, well, why the word scalar? If you just mentioned vector addition, so why not talk about vector multiplication? Well, it turns out that just sticking two vectors next to one another and multiplying them together, you can do that. You could call that the product of two vectors. But unfortunately, it is not meaningful. It doesn't give anything. So what I mean when I say sticking them together, right, is I don't want you to think. I'm going to put this on a totally different sheet because I don't want this written next to me calling this scalar multiplication. If you took two vectors, u and v, and you said, I defined the product u times v to be u1v1, u2v2, u3v2, and u3v3, just like I did for addition, I say that the product of two vectors is this. Well, what's stopping you from doing that? Nothing's stopping you from doing that. But this is useless. This has like no use, it has no meaning, and like no purpose really. So there's no nice property that this thing has. This destroys all geometric data that is going on with these two vectors. And that's why we don't do this. Okay, that's why this is not a product of two vectors. So our notion of multiplying two vectors is going to be more complicated. All right. So first, we talk about scalar multiplication. So first of all, what's a scalar? So quick definition. A scalar is just a real number. Okay, i.e. a constant. Now, here's the thing. In later classes and more advanced classes, complex numbers will be called scalars as well. I see a question about complex numbers that I'll answer in a little bit. But in later courses, complex numbers are called scalars as well, and it's perfectly fine. The reason a scalar is just a constant thing. It's not a vector, i.e. not a vector. Okay. What do I mean not a vector? Well, a vector has more than one component, right? We talk about vectors in R2 and R3, and a vector is we know a point in R2 or R3. So it is not a constant because it's not just associated to one real number, it's associated to at least two, right? Two real numbers in R2 and three in R3. So a scalar is just a real number for us, or just a constant. And so what is scalar multiplication? So let C be a scalar, so it's just some real number, and U be a vector. We'll say it's a vector in R3. Then CU is, I'm going to use the same notation here. So CU is the vector where I have multiplied by C in every component. Okay. We'll do more examples of this when I actually want to see what it is that's going on geometrically. Okay. So there's scalar multiplication. Okay. Now that we know scalar multiplication, I can talk about something which is vector subtraction, right? Now, vector subtraction is really just vector addition, but I'll include it separately. So what is vector subtraction? Vector subtraction, say u minus v, just like regular subtraction of real numbers, is actually addition. It is the vector u plus minus 1 scalar multiplied by the vector v. Okay, but of course, a way to actually write this is I just subtract in each of the components. Okay. All right. Now, the reason I wanted to get all of this out of the way before I talk about geometrically what's going on is now we can actually say a lot of these things that, so for instance, the exact relationship between a vector as the vector between 2 points, and the points could be anywhere in space or in the plane, versus a vector sitting at the origin. Okay, so I have all these three operations now. Geometrically, what do they mean? Okay, so geometrically, what do these operations mean? Well, to see that, we should look to the plane, right? So as I said, it's really, really easy to see this if we look at the plane instead of space. Okay, so let's start out with addition here. So if I have two vectors, we'll say here's u, and v is this vector. Okay, and let's give ourselves some numbers here so that we can compute. So if u is, what does this look like? Maybe we'll say this is 3, 1. So this is the point 3, 1. And what is this? This is the point 1, 4, maybe. That's what that looks like. Okay, so then what is u plus v? Well, this is 3 plus 1 and 1 plus 4. And so this is 4, 5. Where is that point? Where's 4, 5? So here's 3. 4 would be something like this. 5 would be like up here. What's going on here? So this is sometimes called the Parallelogram Rule. Now this is not something you're going to be using pretty much at all in this course, but it is nice to at least know that this is what's going on geometrically under the hood. Is basically u plus v determines the third vertex of a parallelogram determined by u and v. Okay, so this vector you get, of course, emanates from here. So this vector u plus v is the long diagonal of this parallelogram. So here's homework question. Well, it's not really homework. This is just a fun question. So question, what operation gives the short diagonal? Of the parallelogram. So I'll let you think about that. It matters the order that you put these in, so that should kind of hint to what it is, right? We only mentioned a couple operations, so there's not a whole lot of options here. Okay, but what operation gives these? So if u plus v is the long diagonal of this parallelogram, what is the short diagonal? Okay. The answer to this is actually given by what we're going to do here in like 2 minutes. But first, before I see that, I want to talk about something else, which is the geometric picture of what's going on with scalar multiplication. So with scalar multiplication, let's start out with a Let's start out with vector. We'll say that this is the vector 1, 2. Okay, so here's the vector 1, 2. We'll call this vector u. Okay, so u is 1, 2. We already have a u here. Let's make it w. Okay, so w is the vector 1, 2. And now I want to do some scalar multiplying of this vector. So let's start with 2 times w. What is that? So that's 2 times 1 in the first slot and 2 times 2 in the second slot. So this is the vector 2, 4. Where would that be here? 2, 4 would be, well, it would, no, it's a little bit too long. It would be like right here. Forget that for a second. It's all right. 2, 4 would be there. All right. What does it look like I've done? Well, it appears as if I took w, and so this was my original w, but 2w is this thing, right? This is 2w. What about 3w? 3w is the vector 3, 6. So continuing on, this is what I get, the vector 3w, or sorry, 3, 6, which is, 3w. All right, so here's 3w. Now, it seems like it is scaling the length, but wait, let's see here. We haven't talked about how to compute the length of a vector, right? Well, now's a good time to do that, so let's do that, right? So we'll come back to this in a second. How do I compute the length of a vector? So, suppose I have a vector, call it A, that has components A1, A2, and A3. So suppose I have a vector with those components, then the length of A is written as norm A, or length of A. But let's think about it before I write this. What is this? I have a vector here, and I've already put my vector into this form, which means that I'm considering it as a vector with initial point, the origin, and terminal point, A1, A2, A3. So then the length of that vector is just the distance from the origin to the point A1, A2, A3. But then what is that in the distance formula? Well, it makes the distance formula really easy. This is just the square root of A1 squared plus A2 squared plus A3 squared. Why? Because this is the distance from 0, the origin, right, to A1, A2, and A3. Or I'm acting like they're 3 different things. Of course they're not. It's the distance from the origin, 0, and this point, A1, A2, A3, associated to that vector. Right, exactly. So this is the same distance formula that we used in class on Monday. Okay, so this is the length of a vector. Okay. And so, going back to this example, if I actually compute what it is that's going on here, okay, so if I actually compute what it is that's going on here, let's compute the length of w. Right, so let's compute the length of w. What is the length of w? Well, the length of w is the square root of 1 squared plus 2 squared. So this is square root of 5. Right? Okay. What's the square root of 3w? Well, this is the square root of 3 squared plus 6 squared, which is the square root of 9 plus 36 is 45. Square root of 45, but 45 is 9 times 5. Right? 9 is a perfect square, so I can take the square root of that, and what I get is 3 times the square root of 5. So 3w is 3 times the length of w. Okay. So it's called scalar multiplication, and the scalars themselves are called scalars because multiplying by them scales the length of the vector. Okay, it was clear from the picture, but it's nice to see it all written out like this. Okay, here's another thing to consider. I said a scalar is a real number, and a real number definitely includes negative reals as well. What is minus w? Well, when I write minus w as a symbol, of course what I mean is minus 1 times w, but I'm not going to write that to save myself some time. But what is minus 1w? Well, it's minus 1 times each of these components, so this is minus 1, minus 2. What vector is that? Well, this is the vector that is the same length as w, but points in the opposite direction. All right, here's the point minus 1, minus 2 right there. So this is minus w. What is minus 2w? Well, it's minus 2, minus 4. So it is the vector that is twice the length of w, but points in the opposite direction. All right, so here's minus 2w. All right, and so on. What geometric object is the set of all scalar multiples of a vector? Well, I just drew it, right? If I continued going, right, 2, 3, 4, 5, and so on. Of course, even including numbers between 2 and 3 and 4, you know, this is just real numbers. Both positive and negative. What do you get? Well, you get a line. Okay, this is a line. There's only one instance in which you don't get a line, and I'll talk about that here in just a second. Okay. All right. So there is a special vector. Right? There's a special vector, just like there's a special real number for these same operations. So there is the zero vector. What is the zero vector? Well, I claimed that every point in space, every point in the plane, is associated to a vector. So then there must be a vector associated to the point that is the origin. Well, that vector is called the zero vector. So the zero vector is written as 0 with this arrow over it, just like we write with vectors. This is the vector containing nothing but zeros. So in R2, of course, the zero vector is just 0, 0. And what do you notice, right? For any vector u, if I add the zero vector to it, I just get u back, right? And if I take the zero vector and I scale it by any scalar c, what I get is the zero vector. And of course, if I take the number 0 and scalar multiply it by any vector, or scalar multiply any vector by 0, what I get is the zero vector. So there's all these basic properties the zero vector satisfies. And it's useful in many times to talk about the zero vector because, I mean, it comes up in these computations. Okay. All right. Notice that the length of the zero vector is 0. It's the only vector that has length 0. Any other vector has positive length. Okay. Okay. What else? Okay, so we had mentioned that generally, if you just come across a vector, right, sitting out in space, then that vector, right, has an initial point P and a terminal point Q. And of course, we know theoretically that this can be moved to the origin in such a way that P is at the origin and Q is some other point, and that is how we've been writing these vectors. The question is, how can I write a generic vector PQ in the form that we've been using, right? That looks like, I'll call it, X1, Y1, Z1. How can we write it in this form? How can we write it as a point? Okay, here's how. So, if P is the triple X1, Y1, Z1, and Q is some other point in space, then the vector with initial point P and terminal point Q is given by taking the terminal points and subtracting from them the corresponding components from the initial point. So this is x2 minus x1, y2 minus y1, z2 minus z1. Notice, if we do this, then the length of our vector PQ is the square root of, look at this, look at these components. This is x sub 2 minus x sub 1 squared plus y sub 2 minus y sub 1 squared plus z sub 2 minus z sub 1 squared, which is exactly our distance formula in space. Right? Okay. Okay. So I have a couple of more properties to talk about on Friday of generic vectors like this, and then we'll move on to defining the dot product. Okay. So so this is just setting up the groundwork so that we can talk about what all these algebraic properties of these vectors actually means for us. Because this is something that you're going to be using a lot. In chapters 11 and 12, you're going to be using this basic algebra of vectors all the time. Okay. So we will be spending a lot of time on this stuff in the next couple weeks. Anyway, so I think that's it for today. So I will see you all on Friday. No homework will be posted until next week, so you don't have to worry about that. And I know that I've been inundated with a ton of emails in the last few days, more often than, or more. I guess it's been a bigger flood of emails than is usual at the beginning of the semester. So if I haven't answered if you sent me an email a couple days ago and I haven't answered it yet, then I will answer it by this evening. And if I haven't, then you can feel free to send me another one. And that is that. There was one question that I didn't get to. The random question about imaginary numbers in space. I'll talk about that at the beginning of class next time. I'll have a look at it and talk about it then. So anyway, I will see you all on Friday. Remember, you have discussion tomorrow, so your TAs should be sending you their Zoom links. I will put all the Zoom links, just for redundancy's sake, I'll put all the Zoom links on the syllabus. The syllabus page is updated, by the way, so if you haven't had a look at it, look at it. And yeah, I'm going to put the Zoom links there, but also there's the Zoom sidebar that I added in Elm, so your TAs may use that. If they don't, they'll just send you the link directly, and like I said, from now on, we'll have the link in the syllabus. I'll aggregate all of them. Anyway, I will see you all on Friday.